It's a good question.
The thing is about that.
So lecture 4.5, DC motor performance in steady state, which is actually the way that most people think about motor performance is in steady state. So we'll do some analysis and derive motor curves in this lecture, which is kind of the way that most people think about DC motor performance. So, or actually any motor performance, really. Brushed DC motor performance has several aspects, but most of them revolve around the so-called motor curve. Motor curve is, for a given motor voltage, its steady state speed versus a constant torque applied to the load. The test setup for drawing such a curve requires a calibrated, controllable torque source applied to the motor shaft. A brake is typically used. A voltage-controlled magnetic particle brake is ideal. So that would be the best way to get this motor curve. Now, we don't have a magnetic particle brake or really a brake of any controllable torque. And so we don't characterize the motor in the lab that we are doing this week that way. We do a dynamic response. You can still back out some of the parameters that way. But we can still, based on the parameters given in the spec sheet and the ones that we could measure in the lab, we can construct motor curves. So sounds like we have a young student that's out there looking for class. We will gain a deep understanding of DC motor performance characteristics only by tarrying with this situation. Therefore, we begin by modeling it in 4.5.1, this next section, and analyzing its performance in the next section. So, modeling the test system. Including a torque source, TS, on the load changes the model from the last couple of lectures only slightly, as shown in figure 4.10. So what we've done, so the electrical side is the same. A voltage source drives the electrical side of the motor. And then on the mechanical side, we still have the bearing damping, or the motor bearing damping, and the rotor moment of inertia. And we have a torque source that is being applied. So that's the setup. So the torque source that's applied is the brake, and that's what we added to the model effectively. Great. Note that the mechanical subsystem is reduced to only the motor. So we don't have, in the previous lecture, we had the flywheel on there and the bearings, the external bearings. Since during such a test, the load and the external bearings would be detrimental. It is a test of the motor, after all, and not the external apparatus. It turns out that the moment of inertia of the flywheel isn't actually important to remove because it doesn't come into the motor performance curves in steady state, but the bearings would kind of screw it up a little bit because they will come into that final expression. So that only the motor's internal bearings are modeled in this model. Invariant from the previous model are the normal tree, state variables, and most of the derivation of the state equation, so we're not going to go through like an extensive re-derivation of the state model because it's virtually the same as the previous one. So I'll mention the differences. The input vector, instead of being just Vs, is now Vs and Ts, so the torque source is also an input in the system. The continuity equation for the inertia becomes TJM equals negative T2 minus TBM minus TS. The torque specifically opposes motion, to which we assign the positive direction. And the state model's matrices, B and D, change such that A, B, C, and D are listed below. So it's very very much the same model as the previous lecture, but just with one more source in it, the torque source, and the moment of inertia is slightly different, and the one continuity equation is different. So if you are interested in seeing this in this footnote, you can go to that website. Everybody seems to like State Mint. Which one do you like? Number 2, Statum? Yeah, I like Statum too. Statum is the current name of it. And then, yeah, the software name. I think it's probably going to end up being State Mint just because it's way more popular than everything else. I kind of like Stater the best, but people didn't like that one, so I don't think it got a single vote. So I will yield to the voting. Yeah. It was a little bit surprising. I liked State Mint. All 3 of those were my ideas, so I'll take credit for all of them. But yes, good job. Good job, me. But yeah, I am not totally. Yeah, I was a little sad that Stater didn't get more love. I'll be honest. The spelling was weird, but I like the spelling like that. But I'm also not very normal, so clearly.
That's what I don't think I understood what it said.
Yeah, I think every time people looked at the first couple people I talked to about it, when I showed it to them, the word, they were like, ew, I don't like it. But then I was like, oh, it says Stater. And they're like, oh, okay, I kind of like it now. But you had to explain it, so it was like a joke that it's just really not that good if you have to explain it. So it's like all my jokes, too. It's a problem. It really is. Okay, so A, B, C, and D matrices are given here. But the if you want the hyperlink, I didn't type it out here, but there's a hyperlink in the PDF of this that it'll take you to the file that you can use on there. Okay, that gave us the ABCD matrices. So steady state performance analysis. So now we've got the model, we've got our state space model, and now we're ready for some performance analysis. And what follows is actually it's a MATLAB script. Well, I converted it to a MATLAB script and uploaded it to the source page on the Dynamic Systems site where you can download all the lecture files. There's also a source page that has a MATLAB script that does all of this that follows. But I do this in a Jupyter notebook, which is kind of weird, but anyways, you can do it straight in MATLAB too. So that's what the file is that I give you guys, is the MATLAB file. So defining the system parameters. These are the ones that are straight out of the spec sheet for the motor, KT and KV. We're actually going to use those values as the motor constants for the analysis that follows. Their parameters are actually either the motor's a little bit nonlinear, or their specs aren't completely consistent in the manual. They don't give any motor curves, so we're going to develop motor curves, and you have to trust some of their specs in order to develop the motor curves, or you have to measure them yourself. So we're going to trust these specs and see what happens. So T max is in the spec sheet. The max torque is 2.82 Newton meters, and 628 radians per second is the max speed. So the max torque is called the stall torque. And if you were to just grab the shaft of the motor and hold it so it can't move, and you were to run a bunch of current through it, as much as you can, that's the max torque that you can get out. Okay, so no movement. And the max speed is if you had no load, so no braking. You let the shaft go. You don't even have a flywheel on there necessarily. I mean, you could actually, but there's no damping, and there's no external damping, and you just ramp that motor up as fast as it will go, with the voltage, maximum voltage that it'll allow you, and you'll get the max speed, which is 628 radians per second, from the spec sheet as well. I then put in Newton to ounces, the conversion, and then I do meters to inches, the conversion. I just define those quantities, and then I take KT from the spec sheet and I convert it to SI units by multiplying it by newtons to ounces, and then meters to inches, or inches to meters, ounces to newtons, inches to meters, and I get the result in Newton meters per amp. Radians into kilo RPM to radians is this, and so I take the spec kV and I divide it by that, and I get volts per radian per second. The inertia of the rotor and the damping coefficient of the motor are given here, J and B. R is the resistance of the armature, so that's 1.6 ohms according to the spec sheet. And the armature inductance, according to the spec sheet, is 4.1 millihenry. And then we define TF, the transformer or motor constant, to just be kVSI. We could have also defined it to be KTSI. It's numerically the same, and it actually, I checked that, and it is. That part's consistent. In the end, we're going to get a 30% difference in one of the parameters, which is not crazy bad, but their spec sheet's a little inconsistent. It's okay. It could just be that they're all just measured values, one sample measured values, and that's why they're kind of inconsistent. So let's investigate what happens in steady state. So we're going to call that x bar. So we have our state vector, right? X, and it's a function of time. And so that means our states are evolving in time. Our states in this model, let's go back up and review here. The A matrix is a 2 by 2, so we have two states. And if you go way back up to the previous lecture, you'll see that the two states are the angular velocity of the rotor, or the shaft equivalently, and the current through the inductor. Those are our two state variables. So in steady state, those will be constant, or they could be, if you had an input that was sinusoidal, they would be sinusoidal. But the input, let's assume that it's going to be stationary, which is to say a vector of constants. So the system is stationary when x dot equals 0 and u is stationary. So we'll just say u bar. So if we go to our state equation says, I'm using dot here for time derivative, which we like to do, but I try to be a little bit careful about doing. That's our state equation in general, right? What I'm doing is I'm saying this is steady. That means that the state's not changing. So I'm going to say that's 0. I'm going to say that u is going to be some stationary u bar. And I want to solve for what x is going to be, which is also stationary, so I'll call that x bar. So solving for x using just the teensiest amount of linear algebra, taking the matrix inverse, of A and left multiplying it by both sides, subtracting this vector over here, and I get this expression for the steady solution for x, for the state vector. Which is nice because that means we can solve for what our states are in steady state. So what the steady state is, I guess would be a better way of putting that. So let's compute our steady state solution for a constant voltage input, V bar, and braking torque, T bar. We use a symbolic approach to gain insight. So MATLAB is not super awesome for symbolics. I actually really dislike it for symbolics. However, it does do them, so here is a little bit of that. So I define symbolic variables here, B, J, TF, L, R, VS, and TS. And this is just my own idiom, adding the underscore afterwards. It's just so that when I'm in one script, I can define numerical values for all of these parameters in one variable. So I like B and R and whatever can be some numerical values. And then I'll do the B underscore, R underscore, etc. to say, oh, these are the symbolic versions of them. It's just my own convention. It's not necessary MATLAB syntax. And I define the A, B, and U, A and B matrices, and then the U vector. So that's because I'm setting up this, right? A, B, and U. So I'm about to multiply these together. So M1 is negative inverse A times B. So that is negative inverse A times B. And then this stuff is actually, this is just to make things look nicer. So I do M1 separately because I am about to show you guys the full solution, and it's kind of nasty. So MATLAB does not do a great job of simplifying symbolics. Mathematica is much better at it. I much prefer Mathematica for doing symbolics, but I also recognize that you guys probably don't want to learn another thing all the time. It is available in the lab downstairs. It's great. I recommend Mathematica. But I've stopped pushing Mathematica on students all the time because people will push back. So, also Python. I was trying to push that for a while. People push back on that too, so now I'm just like, okay, I'll just do MATLAB, it's fine. And then, so I print out these solutions. So this kind of doesn't look super great. And then also I'll look at the eigenvalues of the A matrix here, which is also an interesting thing to look at. But I don't want to get us distracted by that, so I'm just going to ignore that for now. So a little bit more humanly readable, I'll rewrite these two expressions down here. So omega 2, so we have this solution for the state, omega j and IL. But what we're actually interested in is omega 2, which is to say the motor speed, and I1, which is the motor current. I mean, you could just leave them in terms of omega j and IL because they're equivalent, they're equal. But I just wanted to be very explicit. These are the motor speed and the motor current, and that's why we're so interested in them. That's why I rewrote them as omega 2 and I1, or omega 2 and I1, yeah. So omega 2 is this. So let's dig into it. Well, actually, let's look at the two next to each other first. And then I1 is very, very similar, right? Same denominator with just a couple different coefficients here. So VS and TS both show up, the two inputs show up in both of these outputs, both of these states, I should say, steady states. And there are effectively just like multiplicative factors. TF, R, and BM. Oh, this didn't update. I fixed that, I think. That should be an M subscript on that B. That was a typo. So these are going to be two of the motor curves, effectively. These two solutions will be two of the motor curves. And we're going to dig into that now. So let's focus on the first of these, the relationship between omega 2 and TS, specifically we're going to focus on. So for a given VS, so let's say, okay, I'm going to put in some input voltage like 12 volts or something, okay? And then I want to see what omega 2 is as a function of the torque, okay? And remember, this is the braking torque. So for a given VS, there is a linearly decreasing relationship between omega 2 and TS. This is precisely what some people call the motor curve. I mean, there are several motor curves, but the one that most people will call the motor curve is this relationship. The angular velocity of the motor shaft versus the torque of the load, the braking torque in this case. So it's linearly decreasing, right, with a constant, a slope of negative R over TF squared plus BM R. That's the slope of the motor curve. But it's one of a few curves plotted versus this torque. Other common curves are the current, so we could plot this one as well. So mechanical braking power, so P brake, which is the product of the brake torque and the speed of the output shaft, and the efficiency epsilon. The efficiency is defined as the ratio of the braking power to the voltage source power. So it's weird to think of efficiency as being braking power over the source power, but this is just a test setup, remember? So the braking torque is really the torque you can deliver to your load at any given time. In this test setup, it's a brake, but that's just because you're trying to do a test. But that's the torque that's available, you could think of. It's the torque that's available at that speed. And that's the way that we'll think about this. So the efficiency then is the amount of power that the brake is dissipating over the power that your source is delivering. So how much of that power from the source is being delivered to the load? That's like the real efficiency question. And we're going to plot that too. We're going to plot the efficiency for different speeds and torques. So those are the different curves we're going to plot. We already have expressions for omega 2 and I1 in terms of TS. So that was what we got here, right, in 4.9 and 4.10. We got omega 2 and I1 in terms of TS. As long as we set VS to some constant value, we've got those solved. If we want the other terms, so if we want P brake, the power that the brake is dissipating, we must express omega S in terms of known quantities. From the linear graph, it is obvious that the torque source angular velocity is just the angular velocity of the output of the motor, or the shaft of the motor. Therefore, we can just write it as TS times omega 2. We already have omega 2 in terms of TS, so we're good. And then for epsilon, we know the unknown current source, or we have the unknown current source current, IS, unknown voltage source current, unknown source current, IS. However, from the linear graph, it is obvious that the current from the source is just the current running through the armature windings, I1. And we already have a solution for I1 in terms of TS, so we can just plug that in. So not too bad. Let's compute these quantities for our parameters. So I just define 60 volts for Vs is what I chose, which is common, but not, I would say, not always the one that's used. You can use other voltages. So every time you use a voltage, that generates its own motor curve, and own set of motor curves in this case. T max is TF over R times Vs, which occurs when omega j is equal to 0. So that's something we can analytically solve for, although we could look at the graph and see it too, as we will in a moment. We're gonna generate a vector of torque source values, and we're going to generate a vector of angular velocities, currents, power of the brakes, and efficiency. So that's just the calculation of each of these equations that are above. Now let's plot them. The output is shown here. So let's zoom out a little bit. There we go. If you guys didn't print it out last night, then you don't have your units on the graph labeled, so I would make sure you label them watts, radians per second, amps, and then efficiency is unitless. So here are the curves. Let's unpack them. Let's do them one at a time. So omega 2 is the so-called motor curve, as some people will call it, which is the angular velocity versus the torque. So braking torque is on this axis. The angular velocity of the output's on this axis, the red one. Hopefully you're not colorblind. So the red one is this one, if you are colorblind. And it corresponds to omega 2 radians in radians per second. So you see that as the brake torque increases up to about 3.6, the angular velocity of the output shaft is going to linearly decrease to 0. And that means that it can't deliver more than that amount of torque. So when it's at 0 speed, that's the torque that it can deliver. So that's your max torque, okay, or your so-called stall torque. So this is sometimes called the stall torque. And on the other side of that curve, when you take that torque down to the brake, you let off the brake, let off the brake, let off the brake. The steady state speed is faster and faster and faster, and up to a point where you have no brake applied at all, and then this is the max speed or the free speed. So I would say max speed is often used. Great. And it just varies linearly between those. So you trade off in between here the amount of torque you can deliver to your load and the speed that you're at, which is a very common thing to think about when you're speccing out a motor. You have a sort of choice between speed and torque. You trade them off. At a given operating point, you're going to have to decide if you have torque. It's not exactly the same thing, but it's kind of the same thing. Like when you're out on the freeway, let's say that the speed limit was 70, and then you're going to pass somebody, and then you have a Toyota Corolla, and you try to push on that gas, but it doesn't speed up. You're trying to go past them, but it's like, and it just doesn't go. So what's happening there? You don't have torque at the high speed. You have torque when you go down to a low speed, when you're sitting at that traffic light, and you know that. Let's say like a Ferrari pulls up next to you. You're in that Corolla, man. You just floor that thing, and you got some torque there. But then the Ferrari still leaves you in the dust. But it's not exactly the same thing, because those are actually internal combustion engines. So it's not a perfect analogy, but it actually is effectively the same phenomenon, because even in engines you have this torque speed trade-off. So torque and speed, because they're the two power flow variables and they multiply together to get power, often your power is what you're trading off between torque and speed. So power, it doesn't say constant, but it is harder to get around. So torque and speed are sort of a trade-off. Okay, so that's the main motor curve. Then the next one that we'll look at is the current, I1, so that's the green one here, the other linear one. And that one does exactly the opposite. It increases with the torque. So as you increase the brake torque, and remember, this is not dynamic, this is in steady state. So you increase the brake torque, and then you wait until the system settles into the next position. Then you're going to see these things happen. So if you are braking, if you're applying 60 volts to the motor and you're braking at 3 Newton meters, I didn't put that, did I? Newton meters. Then you would be at this current, so 30 something for your current. So that's the other.
Can you repeat that one more time?
Yeah. So if you brake to 3 Newton meters, so say you have this brake that you can like apply a certain torque, you know what it is. So it's 3 Newton meters to it, and you wait till it settles into a new steady state. Then the current that's going to be flowing through your motor is going to be over 30 amps. So that's corresponding to this axis, the green axis here. So that's significant as well. So that's another thing to think about, is when you have this high torque and low speed, you also have high current. Okay? So for heating purposes, that's pretty important. Also for power delivery from your source, if you can deliver that much. Also, you could violate your especially continuous current rating on your motor. So current ratings on motors, like we saw, it had temporary current ratings, which were much larger. Like for this motor, it was in the 30s of amps for max, but only for bursts. If you want to do continuous, like this test kind of assumes you can do, you have to be much lower than that. So, but that's the trade-off, though. If you're gonna have this much torque apply or delivered to the load, then you're gonna have to do a lot of current. So that's that. Okay, and now we get into the other two curves, which gets kind of interesting. So the braking power is in watts, and remember that the braking power is the product of the angular velocity of the motor, so the output shaft angular velocity, and the torque that's delivered to the load. So it's the product of those two. And so it's the product of omega 2 and the torque. So it's effectively a parabola here, and it has a peak that happens at half of the stall torque. So this is half of the stall torque. And that is the torque that you want to work at if you want to deliver the maximum power to the load. The max power to the load is going to be at the half of the stall torque. And notice that the power that you deliver goes to 0 at these two ends. And that's because when you're at the stall torque, your angular velocity is 0, right? So 3.6 times 0 is 0. Kind of sucks. And then over here, you've got a max speed of 628 radians per second. Great, but your torque is 0. So once again, the product is 0. So in between, you have some power. So you don't have power at the high end, you don't have power at the low end, you only have power to deliver in the middle range. So you don't usually want to operate at the very ends here. You want to operate somewhere in this region. And let's look at the efficiency, because the efficiency is another thing. So you want to deliver a lot of power to your load, but you also want to do it efficiently. You don't want to have to put in a bunch of power and then you might get a lot of power out, but you had to do it in an inefficient way. So let's look at efficiency. How much power do we have to deliver, and how much power do we get out? So the efficiency curve this is pretty typical. So we see that it peaks. So it starts off at 0. So once again, you're not delivering any power at the ends. So the ends are going to be 0 efficiency. And then in between it's going to have a peak. But the peak is really shifted down to low torque and high speed, right? So the low torque, high speed region is where you're most efficient. So what's up with that? Low torque, high speed. There's a trade-off that's happening here, right? We have two different dissipation, I guess, factors here. So if we look back up here, let's look at what shows up in omega 2 and I1, which dominate the efficiency. We've got two different terms that show up. B, the damping of the bearings in the motor, that's on the mechanical side, and then R, the resistance. Those are the only two elements that dissipate energy from the system. So the brake will, but you're applying the brake as in your test setup. So the efficiency of the motor doesn't depend on the brake. The efficiency of the motor depends on how much energy is dissipated by the motor. And if you're running current through a wire with resistance, you're going to be dissipating electrical energy into heat, right? That's what a resistor does. And on the other side, the mechanical side, you have to have internal bearings in the motor, and so there's going to be dissipation in the motor as well from the motor bearings. So mechanical dissipation to heat. So that's where your loss in efficiency comes in. So you've got these two different mechanisms of losing energy from the system. Now, when you're running a lot of current, and so we know how this works. When you're running a lot of current, you're at high torque and low speed, right? So say like you're at this operating regime, so high torque, high current, and low speeds. The speeds are down here, 100 radians per second. So low speeds, the damper. Remember, the damper exerts a torque that's proportional to the angular velocity. In fact, the angular velocity is directly proportional to the amount of heat that's going to be generated. So when you're up here, you're running a lot of current, so the I squared R power is going to be dominant. and you're on the other end where you're going at high speeds and low torque and low current, right? So this region, so the current's low, but the speed wasn't that one, but the speed is high. The damper on the mechanical side is going to be dissipating more of the power. So it's like damned if you do, damned if you don't situation. If you go slowly, the resistor is going to dissipate a bunch of energy. If you go fast, the damper is going to dissipate a bunch of the energy. And so you have an efficiency curve that has a peak in between. And notice that it's definitely, you're way more efficient when you're going fast, when you're in this region, going fast, and you have low current. Because the I squared R current dissipation or energy dissipation on the electrical side kills you at low speed. So these motors are best run fast. Almost all of these motors are best run fast. Okay? So high speed, low current, and low torque. Their efficiencies are much higher there. Maybe you care about max power output more than efficiency. Maybe you're like, I don't care about the energy I'm dissipating in this application. I just need power. You should be operating more here, okay, where the output power is peak. Maybe you're like, I need to operate at the highest speed possible. You need to go over here. Maybe you want to operate at the highest torque possible. You need to be over here. Yeah.
So you said that the highest power would be between the highest speed and the torque?
Yeah, so it's at the half stall torque. So this is the halfway point. That's the max. And I do below a calculation that shows that, but this is TS max over 2, and this is TS max over 2.
And so what would be the case where you would want max power?
So there are a lot of drive applications where you're like, I need to flow as much energy into the system as I can. So I mean, any sort of like, I guess, electrical car, automotive situation where you want to be operating at you want to be delivering the most power to the load, that would be where you want to be. If you wanted to have, but say you're in a situation where you need to like haul an electric vehicle again, you need to get some big heavy load moving. You want to be at max torque. Say that you want to be operating at max efficiency, like an eco situation. We're trying to conserve energy. You want to be operating at max speed. Not quite max speed, but in this max efficiency spot, which is close to max speed. So that's like the different operating regimes. You want to be in different places depending on the application that you're using. Yeah, question.
I didn't know if you were finished.
No, go ahead.
You said the most efficient is at low torque and at high speeds.
Yes.
Low current.
Exactly. So right there is your max efficiency, and so you're sort of trading off and operating. So one of the things that you'll do is, say you're gonna maybe you want to drive this motor at just one speed most of the time, but you don't want to have such low. So you want to have that high efficiency. So you want to drive it at high speed for the high efficiency, but you actually don't need it to be going that fast, and you want to have more torque. Okay, so you want to have your cake and eat it too. So then you gear it. Okay, so what you can do then is have your motor operate here, and then you have a gear train that slows it down Okay, and the gear train, remember, when you have a gear, well, 2 gears, what you can do with 2 gears is you can trade off speed and torque, right? So say you're really interested in working efficiently, okay, so you want to be operating your motor here, so you don't want to dissipate a bunch of energy in your motor, but you also need more torque, so you don't want to trade off the 2, which is what you would have to do if you just use the motor directly. Then you have to put gearing on your motor output, which is why so many motors have gearing gearboxes in the output, because you end up operating at well, for different reasons, but one of the main ones is that you can operate at a more efficient location in your motor curve, and still get the torque out that you want. There are other reasons as well, which is maybe you need more torque, period. That would be another one. Or maybe there are some applications where you need more speed, which that's usually not it, but occasionally it can be. So, yeah, okay. I'm keeping you guys late, so I'll let you guys go. Enjoy your weekends.
You too, Dad.